Hello, so these are the oral tryout part 2 solutions. So yeah, I guess I'll just get started on them. Exercise 1 was pretty trivial if you knew what you were doing. B was literally just A, but just more generalized. So, oh god. Okay, cool. So basically, if you want to prove that there exist no integers A and B such that 12A plus 48B equals 1, it's pretty easy to just say that, hey, you can factor out a 12, so it just makes it A plus 4B is equal to 1. Then A plus 4B must equal 1/12. But since A and B are both integers, that means that, it's just an integer plus an integer. This is a real, right? It cannot. It can't be true. Because an int plus an int cannot equal a fraction, so it's false, right? So that's just it. There's no integers a and b such that if you add them in a linear combination, they equal a fraction. Now for here, it's pretty much the same thing. There's GCD of a and b. Let that equal to just some integer k. K cannot equal 1, and therefore k must be greater than 1, right? So ax plus by must equal to 1. Factor out a k, you have a over k times x plus b over k times y is equal to 1. Same rationale here. If k is greater than 1, then 1 over k must be less than 1. And since k is positive, then 1 over k must also be positive, right? So therefore, 1 over k lies in the interval of 0 to 1. Therefore, 1 over k is just some fraction, right? Is a fraction. Well, I mean, I guess calling it a fraction will not necessarily be the right thing. Is rational, but not necessarily an integer. And since k is a GCD of b and a, k divides both a and b. Therefore, a over k and b over k are integers, right? Right. So because of that, that just means that they're like integers. So same rationale here. An integer plus an integer cannot equal a fraction. So therefore, no a and b, right? That's just your whole proof. But yeah. Okay. Exercise 2. Okay, one sec. Okay, so exercise 2 is just saying that you need to find a positive integer such that. So consider this, right? If n is a positive integer and b, what having a non-unit or non-zero units digit means is that b doesn't divide n, right? Why? Because in the base b representation, you'll have something like b to the n plus something else. I should probably just use x plus y times b to the n minus 1 plus something. And then that non-zero unit digit, let it be z, times b to the 0. This just means that it's a remainder, right? That's what the unit digit is. It's just a remainder when you divide by the base. So because of that, you just have to say that, hey, b doesn't divide n. And because of this, anything b to the n will also not divide n, right? It's pretty easy to think about, logically, because think about it this way, right? If n over b is not an integer, right? Is not int, then n over b squared, n already doesn't have any b's. So n over b to the n will also not be an int. So that's pretty much just the reasoning you want to use here. So yeah, you don't have to do all this explanations. I'm just kind of showing the actual full thing. I would have probably saved a couple corners if I was presenting this in orals. 3 is just the derivation of the n choose r formula. Hopefully everyone already knows it, but essentially when you're choosing r objects, you have r objects, right? Say this is of length r. Then you have n choices for the first one. You have n minus 1. You have, here, I'm just going to draw like 1 or 2 extra things. Then you have n minus 2 up to, you have n minus r plus 1, right? It's n minus r plus 1 because, like, it's just n minus r. Yeah, it's just like n minus r plus 1. Because, why? Because this extra stuff is the complement of that. So you just don't have to, like, you have to make sure you include that plus 1. Now, where do we go from here? Okay, so that's the total choices you have. And another way of representing that is literally just n factorial over the things you don't want, which happens to be n minus r plus 1, which is just n minus r, right? Or that's the stuff you don't want. Or no, there's factorial here, right? So this is like basically the total amount of choices you have. But since you're choosing r objects, you got to realize that, hey, the order also matters. So because of that, you're dividing by something else. You're dividing by the total amount of orders of this. If you have r objects, how many different ways are there to order them? It's just 1 over r factorial. So that's just equal to n factorial over r factorial times n minus r factorial. Yeah. So that's pretty much it. I know I kind of was, I may have said it a couple like wrong, but yeah. Okay, exercise 4. Okay. So basically for the sum of all the factors of n, you got to consider the sum. Any factor is some combination of p1, p2, all the way up to p of n, right? So if we want all total possible combinations, we consider all possible choices, right? Choice 1, right? Let's just look at p to 1. The choices we can have are either p1 to the 0th, p1 to the first power, or p like up to p to the n, right? Those are the total amount of choices we have. Now for all primes, this is up to p to the n. Sorry, this is not. This is supposed to be e to the 1. We'll have, again, p to the n. We'll have either, we could not include it, we could include it once, or we can include it up to the amount of times which shows, which is just p to the e to the n, or e sub n. So yeah. So now those are all our choices, and if we want the choices of the element, it's literally just like add them together, right? Or multiply them, right? This is kind of like, if you ever heard of generating functions, it's kind of this like rationale, where it kind of like, hey, I can represent all the choices just an expression. So you have p1 plus p1 squared up to p sub n. Or no, p1 to the e to the n, sorry, or e to the 1. And then that's just one term, right? Now we're doing it with another, like we're doing all the things in the middle up to 1 plus p sub n squared plus up to p sub n e sub n, right? That basically guarantees that any possible combination of all the primes will get us the thing. So what do we have to find? We have to find an expression. If you leave it like this, I wouldn't really care. You could also use summation notation, which would just be the product of all these terms, right? So that's just a big pi, capital Pi, denotes product. Where are we starting from? We're starting from, just say like I starts at 1 and I goes up to all the amount of primes you have, which is n. Then within that product, we're just doing the sum, which is this normal summation notation. That would just be of the prime, so I'll just say k. That'll also start at 0, because remember, this is just equal to p sub 1 to the 0th power, and we're going up to e sub I. So that, and then we're adding just take the prime, right? The prime number. Take whatever prime number we're at, which is the I, and raise it to the k power, which is just, oh crap, which is just that. So yeah, that's the expression you're looking for. Yes, that is it. So yeah, pretty cool. If you use summation notation, that's very cool. If you didn't, I didn't really care, but it's nice to show that you know what it is. Yeah, okay. Then moving on, the product of all the factors. Sorry, one sec. Okay, cool. The product of all the factors, you didn't actually need to overcomplicate this. Consider this, right? For part B, all the factors come in pairs. And so you might be like, well, if it's a perfect square, not all factors come in pairs, right? I'm going to show what happens in 1 second. But basically, since all the factors come in pairs, say we have a number n, and we have factor 1. The other factor is guaranteed to be n over a factor 1. Call that factor 2, or just leave it as n times factor 1. So say if we take all possible factors, or I'm just going to say like half of the factors, like f of the number of factors over 2, all of them are just going to have some factor pair to it, right? So what am I trying to say? Since all the factors come in pairs, if we literally just do, like, and they all guaranteed to be multiplied to n, right? f1 times n over f1 is equal to n. Whatever is, like, that's also equal to n, right? So we just do n to the amount of factors we have. That would be the amount of pairs we have. But you want to just find the product over factors, which is just over 2. You're just dividing because there's 2 in a pair. So literally, this is it. And what is f? F is just number of factors, which you can find pretty easily just by like using the prime factorization and then just doing that stuff. It doesn't say you have to do it in terms of your variables. If you needed to, it would just be 1 plus e1 times 1 plus e2. So yeah, it would just be that. You could just say f is equal to n plus the sum of whatever this is, just 1 and e, right? E sub I, right? It would just be that. So yeah, that's literally just the entire problem. But yeah, okay, cool. Oh, we still have a lot of problems left. Oh, I should probably not be talking so much. Okay, so for problem 5, prove the identity. There's 2 ways of doing it. You can either use the idea of subsets, which I'll show. Basically, say you have a set of size n. So it'll just be like just 1, 2, 3. It doesn't matter what's in the set, just as long as it is a set. Then the 2 to the n is total subsets, right? Another way of calculating total subsets is, hey, how many ways are there to choose 0 elements? So that's just n choose 0. How many ways are there to choose 1 subset? That's n choose 1. And I hope you get the idea here, up to like how many ways are there to choose n total subsets? Just n choose n. So both of these mean the same thing. There's just the amount of total subsets, therefore they're equal. All right, that's one way of showing it. The other way of showing it, I actually didn't know of this until Suki showed it, which is pretty cool. You can use the idea of binomial theorem. So so you know that x plus y to the n is equal to x to the n plus n choose 1 times x to the n minus 1. Actually, there's an n choose 0 in front of here too. N choose 0 times x to the n plus n choose 1 times x to the n minus 1 times y plus n choose 2 times x to n minus 2 times y squared up to n choose n minus 1 to the x to the 1 times y to the n minus 1 plus n choose n to the y to the n, right? That's equal to that. That's just binomial theorem. It's just a formula. Something cool is that, hey, if you let x, y equal 1, both of them equal 1, then you just have 1 plus 1 to the n is equal to all of these turn into 1, right? No matter what. So you're literally just with the n choose 0 plus n choose 1 plus up to n choose n minus 1 plus n choose n. Well, this is just equal to this, and then 1 plus 1 to the n is just equal to 2 to the n. So that's another way of doing it using binomial theorem. Okay, next problem. This one's pretty personal to me because oh crap. 1 second. Yeah. Okay, so I think I accidentally opened something. Yes, I did. Okay, did not mean to open that. Next problem, I actually got asked for my first ever orals competition back on Meet 1 of my junior year. And I got almost all of it right, except for the if and only if part. You'll see that if and only if. I only proved the if. I didn't prove the only if. I lost 4 points that day. Very, very sad. But yeah. Okay, so basically, it's just the divisibility rule of 7. That's the whole problem. So you need to show that if 10a plus b is congruent to 0 mod 7, then a minus 2b is also congruent to 0 mod 7. And then there's a if and only if part, which I'll explain after. But basically, take 10a. You can just manipulate 10a plus b into what you want. So that's just 7a plus 3b plus 7b minus 6b, because you're trying to eliminate stuff. Those 7s cancel out because 7a and 7b are guaranteed to be 0 mod 7. So get rid of those. So you have 3b minus 6b is congruent to 0 mod 7. And then you can just cancel out or factor out that 3 and just show that 2. No, just show that. Sorry. This is supposed to be an A. I made the mistake when I was showing it to someone else too. But A minus 2B is congruent to 0 mod 7. Now, you show that those are equal, but the whole point of if and only if is that you need to, to prove that something is true if and only if something else is true. You need to prove that for 2 things. The first one is if A, then B, right? The second thing is if B, then A. So let A be, what is it? 10 plus B. 10A plus B is congruent to 0 mod 7. And then let B just be A minus 2B congruent to 0 mod 7, right? If these two are true, well, we show that A, 10A plus B is congruent to A minus 2B mod 7 because they're the same expression. So that means that if 10A plus B is not, if this is not 0 mod 7, then this is also not 0 mod 7, right? And furthermore, if it is 0 mod 7, then this is also 0 mod 7. Therefore, we've proven the if and only if, and that just concludes the proof. So, yeah. Okay. Next one. Okay. So this one's actually really nice. I'm actually really mad at myself because I didn't ask this to anyone. But, yeah. Basically, you can take a polygon with n vertices. So first case is A, take a hexagon. Take a hexagon, and the radius is just r. And then this would be theta. So you can just use the idea that the area of a triangle is just 1/2 r squared sine theta. And then multiply this by the amount of triangles you have. So 6 times that. And so you have 6 times 1/2 1 squared times sine of what's 360 over 60. Or 360 over 6 is 60. So it's just 3 times sine 60, which is just root 3 over 2. So just, is it? Yes. 3 root 3 over 2. Now for part B, it's kind of similar. Just let's take this formula and kind of manipulate it to what we want. 6 is n, so n triangles times 1/2 r squared sine theta, but you're not allowed to use theta as a variable. So what is theta even equal to? Well, total amount of angles in a full 360 revolution over the amount of partitions we have, which is just n. So this is just the general form of a regular n-gon. And now we have to show that as n approaches infinity, what happens? Well, Sweller, it's a circle, right? It's pretty easy to think of in your head. But to rigorously show this, you just need to say that, hey, the limit as n goes to infinity of n times 1/2 r squared times sine of 360 over n. Well, what is that? Well, first of all, 1/2 r squared are constants. So r squared over 2 times limit of n approaches infinity is just, and then it's, and the inside is everything in terms of n, so n times sine of 360 over n. So now what? Well, this is kind of a weird limit to solve, but if you use L'Hospital's rule, or L'Hopital, then you can just rewrite this as sine of 360 over n over 1 over n, right? And then to solve that, well, take the derivative of both. It's just cosine of 360 over n, and chain rule also gets the 360 out of here. And it also gets the derivative of 1 over n, which is just negative n to the negative 2, right? Yes. So then this is all over the derivative of that, which is just negative n to the negative 2. So just writing some of our other stuff that we need to show. This cancels out with this. This cancels out with this. You can take that 360 out. And this, now I mentioned that, hey, we're right now in degrees. In a formula, like, you don't really multiply something by 360. You multiply it by radians. So I'm just going to turn that negative 360 into, the negatives cancel out here. I'm going to turn that 360 into a 2 pi. So that's 2 pi r squared over 2 times the limit as n approaches infinity of cosine of 360 over n. Well, as n gets really big, this just turns into cosine of 0. That's also why we use L'Hospital's rules, because we know that this equals to 0 over 0. That's something I forgot to mention. But yeah, this just turns into 1. So just 2 pi r squared over 2 times 1 is just pi r squared. That's the final formula, which is also the area of a circle. So yeah. Okay. How many more problems do I got? Okay, one more. Okay, this one is pretty cool. It's not too bad. It's just geometric probability, like the geometric distributions from stats. So P of n, the probability that's divisible by 2. Well, one second. Wait, something is. Sorry. Okay, I was just getting like text of someone. I got distracted. But essentially, for m of n to be divisible by 2, we just need to show that, hey, the complementary probability shows that for a, the probability of it getting, like, it's very hard to like show that it gets divisible by 2 because there's so many different ways to get a 2 in there. But on the other hand, what if we don't have a 2? Well, that's just 1 minus the p of not getting, or of no 2, right? That is equal to 1 minus the probability of it not being an even integer, which is, well, what are the even integers that we have? We have 2, 4, 6, and 8. So that is just a 5 out of 9. And for the number of times you get it. So that's just a 1 minus 5 over 9 to the n. B, with very, very similar reasoning, the divisible by 5, well, there's only one number that is divisible by 5, so that's just 1 minus 8 over 9, the complement minus n. Now for C, Derive an expression. So for divisible by 10, it can't be divisible by 2, and it can't be divisible by 5. Yeah. But so it would just be 1 minus the p of no 2, sorry, and p of no 5, right? So the probability of, like, okay, so if you think about it, p of a and b in general is just p of a plus, or no, p of a plus p of b minus p of p of a and b, like the intersection. I just realized that this is or, not and. So yeah, that's just it. So now we can just plug that into p of, or the probability from above. So that's just p of no 2, which is 5 over 9 to the n, minus, or no, plus the p of no 5, which is 8 over 9 to the n. This entire thing is in parentheses, by the way. Minus the, like, both of them combined, which what numbers don't line the set? That is just going to be 4 possible numbers over 9 to the n. So that's just your p of a and b. So just distributing that out, you just have 1 minus 5 over 9 to the n minus 8 over 9 to the n plus 4 over 9 to the n. So yeah, that's the final formula. So yeah, pretty nice problem. So that's pretty much it.